This meeting is being recorded.
There we go. Okay, so hi everyone. Good to see everyone. This time I'm going to do things just a tiny bit differently. I want to start off by saying thank you to Ryan for his last presentation. I kind of stole aspects of his format, namely copy and pasting, well, like copying things from the book saved me a lot of time on like actually, you know, rendering each individual object. And I also have a notebook with code that will be following along with as well. I am assuming that everyone has hopefully read this chapter, so I'm going to leave more time open for, you know, comments, questions, and basically more like a discussion of, you know, how we've seen this implemented in practice and maybe any additional insight that people can add to the group. So just keep that in mind, and if nobody comments, then it might be actually a shorter meeting than one would expect, so keep that in mind. But I'm going to start the slideshow, and I'm going to flip between this and the code, some of the exercises, so let's start. Okay, so Matrix Decompositions, Chapter 4, by me, with San Diego Machine Learning. Okay, so really quickly, I'm just going to go over sort of like, you know, the definitions of things and the intuition that I have, and then we can, you know, discuss maybe other people's intuitions and like, you know, notes pertaining to the material. So starting off, you know, the book went over the determinants. And I realized that for formatting, it actually deleted the equations for the 2x2 and 3x3 determinant. Wonderful. But I'll show you that in the code. Basically, how I see the determinant is a measure of volume defined by the individual vectors in a matrix. And by that definition, it should follow then that, you know, determinant is associative. So the determinant of AB is, you know, can be expanded, the determinant of A times the determinant of B. It should also make more sense why, you know, the determinants of a transposition is the same as the, you know, original matrix. And then why, actually something very important is that similar matrices have the same determinant. Oh, sorry. Similar matrices have the same determinant. That's something that I've actually found to be very useful in calculating the eigenvalues and eigenvectors. And I can actually go into my solution in a bit as well, but that's something really important to keep in mind. Also, I think one of the things that wasn't immediately intuitive is that scaling, when you scale, you know, the matrix, you have to scale it by the exponent exponentially by the dimensions of the matrix. But that kind of makes sense, you know, when you assume that you actually have to scale that volume n times, sort of like, you know, squaring or cubing, etc. You know, volume versus area, and then swapping two rows or columns changes the sign. Oh, there it is. Great. Okay, so the 2D determinant. Yeah, I'll show these three equations in the code in just a second. So
you might want to like just pause and like see if there's anything.
Oh no, of course. I was just going to go over the traits first, real quick. But yeah, before I pause and I go over questions, etc. Just want to quickly talk about the trace because it's fairly simple concept, but I feel like it's one that's incredibly valuable for a lot of other different things. But it's basically just the sum of all the diagonal elements. It should follow kind of intuitively, say, why it's you know, associative over addition, you know, why it's scalable in that way, because it's just, you know, a sum of numbers which can be boiled down to a scalar value. And then the trace of the identity matrix is just n, you know. So now I'm going to take a second. And first off, I think I'll ask for questions now. Does anyone have any questions pertaining to determinant, trace, or anything?
You only add that determinant, if determinant is equal to 0, then the matrix is not full rank, so there is a linear dependency between columns.
Yes, that is important to know.
I know it will be next.
Yes.
Probably will be next.
Yes. But that is an important thing to note, is that from chapter 2, if the determinant is equal to 0, then the system of equations is linearly dependent. And actually, if I can go back to, there isn't a good intuition to be derived from this. If we can see here that it, we're talking about a volume here. Say if we have like two collinear vectors, maybe if this B vector was pointing in the opposite direction, and it was just that, and then a collinear vector, and then this one right here, it wouldn't actually have a volume. It would have an area, but it wouldn't have a volume. So it wouldn't have a value in n-dimensional space, and that's kind of how I'm thinking about it right now. Is there anything else anyone would want to add to that? Any question?
I have like 2 comments. I hope people can hear me on your microphone. I can unmute, but then they'll hear both.
I'll mute my microphone really quick.
So, in terms of what you just said about thinking about this as like a volume, so if you map the unit cube to this new volume, if it's full rank, like you were saying, then it's a 1-to-1 mapping. If it's not full rank, then what you're going to do is you're going to map multiple points in the cube to the same point in the lower dimensional space. And then in the reverse direction, now you don't know which way to map it because there's multiple points that all got mapped to this. So when I try to invert the mapping, it's now a 1-to-many instead of a 1-to-1. So this is why, geometrically, why if the volume is 0, you can't have a easy, fully specified reverse mapping the inverse. Okay. If you have an inverse matrix, then basically that defines the reverse geometric mapping back to the original cube. But once you go many to one, there is no way to undo that problem. Does that make sense for everybody?
How does that, if you don't mind me asking, how does that contribute to the determining 0?
So anytime you reduce the dimensionality, your volume will drop to 0. So if you have a 3-dimensional cube and it gets mapped to a plane, then the volume will be 0. If you have an n-dimensional and it maps to n-1 or n-2, the volume, again, we have to sort of say what is volume, but the n-dimensional volume will be 0. And that's a sign that you've lost rank. And as soon as you lose rank and you go many to one, you can't invert that operation. So just like x squared, if you say, well, I can map 3 to 9 and I can map -3 to 9, but then when you have 9, how do you go backwards? You just can't. Okay, because you sort of lost some, dimensionality there. So that's how I would say that what both of you said about the geometric intuition like applies to invertibility of the matrix. Yeah, Tony, right?
And just to expand on that, if you think of it like an image or Photoshop, you have a bunch of different layers, and then you flatten it out as a JPEG. You can't tell what was behind any of the pixels because you're no longer storing that.
Yep.
Right. Interesting. Okay.
Yeah. So I like that geometric intuition, but the other thing that I'll say is that for me, the trace, okay, yeah, it's obvious that the trace of the sum of two matrices is the sum of the traces, but that the properties of when the trace is invariant, for me, that still occurs a little bit like black magic.
When it's invariant?
Yeah.
Well,
I don't even remember because you see, I don't have it that well. But there are places in the book where they say like these matrices will have the same trace, right?
I think I have an example of that.
Yeah, yeah. And they do have this geometric intuition where they say it's like the perimeter of the rectangle. But still, like if you think of it as volume, and then I think of like the eigenvalues are, which we haven't gotten to yet, but they're going to multiply together to be the volume, then if you have the same eigenvalues, no matter how you reorder them, the volume will be the same, the determinant will be the same. Okay, I kind of have a geometric intuition on that, right? But it just seems to me like, but the trace is just the diagonal. Like you just do a little bit and all of a sudden you have different numbers that happen to live on the diagonal. It just seems like, wow, I'm amazed that that works. That's just me. So I'm open to anybody that has better intuition around the properties of the trace. Again, the way it's calculated as being on the diagonal, I'm very clear that if you multiply the entire matrix by 2, you've doubled everything on the diagonal. Yeah. But what that really means, that's the hard part.
Yeah, so I do, and I'm turning my volume back up. Okay, cool. Yeah, I have an interesting example of that happening. That's a little bit off book, but I'll get. So sorry, it is a little bit off book, but it is interesting. So, but I will get to that in a bit. So, moving on, or actually, oh, sorry. Before I do that, I'm going to show you just a little bit of the what code for this kind of looks like. Let me see if I can move this over. Linux. Okay. Cool. So this is my Google Colab notebook. I think the saturation is up really high because you can't really see where the cells end. But all right. Yeah. So this is basically from the book, right? So for two-dimensional matrices, the determinant is just like sort of in this minus this, or A times A minus B times B. But for in 3 dimensions, it's Sarris's rule, which incidentally I did not actually calculate correctly here. But I think the general idea of it is very is like to add these and then subtract, right? So ignore this. I didn't get a chance to actually go back and fix that part. But kind of from a larger or in a more general sense, this idea of Laplace expansion. And so I just kind of calculated it. It's a recursive algorithm, which is a wonderful excuse to use recursion. Don't get too many of those. But you can kind of see here that like the determinant of an identity matrix is just 1. And why is that? Because you just have 5 unit vectors essentially forming like an orthonormal basis or an orthonormal matrix. And so that just equals 1. But this kind of like recursive algorithm, to be quite honest, I am not 100% like intuitive familiar with why this works. But all what I do know about it is like, you, for like the top row, recursively ignore the top row, and for each index, ignore that column, calculate the determinant of the rest, multiply it by a sign of 1 or -1, and then sum those values up recursively to find the determinant. And that's just about what I did here. Now, of course, I hard-coded the 2x2 determinant, but it's, besides that, I just did the Laplace expansion here. And then they did this by hand in the book, more or less. And you can kind of see here how that's working. You're inverting the signs, or you're, what's the word? You're oscillating. You're oscillating the sign, and then computing the inner determinant and using that to find the solution. So I tested out my solution, and fortunately, it works. I don't know how many people did the exercises, but I did not check that the answers to these exercises were correct. So if anyone right now wants to tell me that this is not working and my algorithm is bogus, that would be the time. Did everybody get these 2?
What was the answer for the determinant?
Uh, oh, right. Oh my goodness. I did this like,
What was the question?
there were determinant exercises, right?
Yeah, like the first two problems, I think. 4-1 and 4-2.
Yes.
No, I thought you had the problem numbers down below.
I did, but I think I just started putting the problem numbers because I did this part like 3 weeks ago. I think these are the exercises actually, if I'm not mistaken, right?
No, scroll down. I thought I just saw where you said.
Because these are wrong. The Sars's rule is wrong. It's the only thing in this that is not validated or that is wrong.
No, keep scrolling. I saw explicit. You just said 4.1, determinant 0.
Yeah.
And
oh, is it? We start. Oh yeah. Sorry.
exercise 4.1,
no,
0.
Sorry. Yeah.
And then exercise 4.2.
Yeah. Sorry, my bad. No. So.
Same thing.
Okay. Okay. Good. Awesome. Okay. So. And yeah. So that I trusted that. Cool. Okay, so any closing remarks regarding the exercises or determinant or trace? Okay, I'll move on now. Okay, so now on to eigenvectors and eigenvalues. So just to really briefly go over this, eigenvectors and eigenvalues, they hold that you can multiply a vector by an eigenvector and it will equal the scaled version by its eigenvalue. This is also equivalent to the solution set of A minus the eigenvalue times the identity matrix equals 0. And as you know, talking about earlier, the determinant of this equals 0. So something, and that follows that suddenly the rank of A minus this eigenvalue times the identity matrix is now less than n. So it's less than the rank of A, because an eigenvalue, multiplying it by the identity matrix and subtracting it, makes this system of equations, or this matrix A, linearly dependent. And to me, that says that it represents the relationship between these various vectors and can be used to define the null space, because this is a homogeneous set of equations here. So this is like, so that's how I kind of see it personally. Another identity that they gave in the book was that the product of all the eigenvalues equals the determinant of A. Now I had to think about this for a second, like why is that the case? But it goes back to, something very crucial and fundamental, that similar matrices have the same determinant, they have the same eigenvalues, and they have the same eigenspace, I believe, yes. So basically, you can write any square matrix as either, well, actually, this only holds for full rank matrices, right. But with others, it's defined by, you have like the eigenvalues as roots of the characteristic polynomial. And there's a bigger equation for that later, but just in this case, we have this equation A equals P inverse times D times P, where P is the eigenspace and D is the diagonal matrix of all the eigenvalues. And so in this case, the diagonal matrix of eigenvalues is similar to the original matrix. And seeing as that's just diagonal matrix, each of the columns has its own coefficient, I suppose, it should make sense then why all of these vectors multiplied together equals the volume, is equivalent to the volume of the original matrix. And so that's kind of how I, see it. And then just a couple of definitions, set of all eigenvectors is the eigenspace. And then the set of all eigenvalues is the eigenspectrum. And then the dimensions of the eigenspectrum is the geometric multiplicity. And I'm going to get into why that is important when we talk about diagonalization. But I mean, it's important otherwise, but basically comparing the dimensions of the eigenspectrum, I'm sorry, that's supposed to be eigenspace. Whoops. The dimensions of the eigenspace is comparing that to the rank of the matrix is important. So in the talk about this second, because characteristic polynomial kind of seems like a way to solve, and get the eigenvalues and the, eigenvectors. But so that's why I'm just talking about this really quickly now. You can get the same equation. You get the determinant of a minus lambda I equals 0, and then you get the solution space. C0 here is the determinant of A, and then each of these terms after is, plus or minus the trace of A. That's what it says in the book. I actually forget the intuition behind this part, but this is one way that you can solve for eigenvalues and eigenvectors. And I'm assuming if you all did this from the book, this is probably how you solved for it. And I'll kind of show in just a second what I did as far as solving this with code, because it's very similar and kind of different at the same time. But algebraic multiplicity being the number of times that each eigenvalue is the root of the characteristic polynomial, or when it equals 0, and then that is how strongly it influences the structure of the matrix. And a defective matrix has one eigenvalue with an algebraic multiplicity over 1. Defective meaning not full rank. And so that could kind of make sense. But I forget how to articulate that. But it just and actually, would anyone else have an explanation on how to articulate that?
I would not have an explanation, but there's a phrase Markov chain that comes to mind.
Does it?
I don't know if that's the appropriate way to do it, but I was thinking of Markov chains. If we get a stable set versus expanding divergently or going to 0 negative, if there's any connection there.
Yeah, no, I think in the book they say that there's the theorem where if the eigenvalues are all unique, then their eigenspaces are all one-dimensional, and they're all guaranteed to be orthogonal. So in order for you to have a problem, then one of them has to be at least 2-dimensional. So that's the greater than 1. Okay.
Interesting.
Yeah,
Okay.
and then the other thing that I was thinking about reading this chapter is that if you have an eigenvalue with multiplicity 2, let's say, okay, then the eigenspace for that defines plane, and a 2D plane has 2 basis vectors, okay, and any 2 linearly independent vectors that lie in that plane are a valid basis for it. And depending on what technique you learn for finding the basis for that eigenspace, there's no reason why that technique requires that your vectors be orthogonal. You always can find a pair of vectors that are orthogonal that define that plane, but the technique that you were taught won't automatically give you orthogonal vectors. So I believe there's a point in the book where they say, hey, let's find a basis for this 2D space, eigenspace, right? And they're like 1, 1, and 1, 0. great, that worked, but they're not orthogonal, and we would like orthogonal vectors. And so then you can do Gram-Schmidt, and you could say, I will find an equivalent basis that is only orthogonal vectors. So, but it took me a minute to figure out, like, wait, why is it that when they're all multiplicity 1, they're all orthogonal, but when it's more than 1, then they're not? And like, oh, it's not really that they're not in the mathematical sense. It's just the technique I used for finding them didn't force them to be orthogonal.
That's interesting. That's very interesting. No, that makes a lot of sense, actually. With that in mind, did anyone have any questions or comments regarding eigenvalues or characteristic polynomials? Any additional insight? Like, does anyone have a story of the last time, he used an eigenvalue or eigenvector? I mean, I know that they're, use them a bit, but like, if anyone wants to share anything.
Kind of use them for PCA, principal component analysis, as a linear reduction.
Yep, definitely. In fact, they mention in the book that these are used for PCA, and these are definitely used for PCA. So,
yeah. And that's going to be chapter 10 of the book, by the way.
Yes. Yeah.
I'll say that I'm fond of reading papers that are about trying to understand how neural networks work, or why this technique works better than that technique, or whatever. And spectral analysis of the eigenvalues does come up reasonably often, and I find that sort of forced me to go back and review my linear algebra and eigenvalues and like, how well do I understand this? I'll also say that I took linear algebra many years ago when I was in college, and I was able to understand the section about eigenvalues. But I think if you're someone who never saw this material before, then it was presented super duper fast, and you shouldn't feel bad, because in a normal linear algebra course, it would be presented over like, 1 or 2 chapters, what is like 3 pages in a subsection in this book. So that's again where it's like, this is a great book at reinforcing here key concepts that come up in ML. But if it's all really brand new to you, you might need to look elsewhere for something that goes a little bit deeper and slower and doesn't just say, bam, 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 here are all the theorems and conclusions.
Yeah. And actually, one thing that I would suggest actually is 3 Blue 1 Brown's linear algebra course. Very, very intuitive, very good. Like his visual, mapping of, say, like determinants, eigenvalues, eigenvectors, were very helpful to me over time. And actually, if anyone doesn't know this, the library that he uses to make his, he's published or made open source the library he uses to actually make those animations. So if anyone, has a presentation to make, and they want things to move around and be super cool, something to take a look at. Oh, for 3 Blue 1 Brown, or for that package?
Yeah.
Oh, I don't actually have it on hand. I'm sorry. I probably should have, but actually, really quick, what I want to talk about is like this eigenspectrum, because I know that this is not something that I have personally analyzed yet. But the example that they gave in the book is they have this like neuron connectivity matrix where they're quantifying how different neurons relate to each other, and they have neurons on one index and the same neurons on the other index, and then the activation, or the activation, whatever you want to call it, the number is how correlated or coupled they are, and getting the eigenvalues of this particular matrix in descending order, because that's how they usually show up. I am kind of curious, to everyone in the room, what you can do with a graph like this, with like a graph of eigenvalues, what sort of, math you can do to say certain things about this connectivity matrix. So I'm kind of curious.
It's all Minesweeper.
Aren't the values related to the importances of the?
Yeah, so how I understand it is there's, yeah, so it's a value of 1 if neuron I talks to neuron J through a synapse, and 0 otherwise. So.
Right, then the eigenspectrum has a value associated with each
Yes.
eigenvector.
Yeah, it doesn't show the eigen space here. It just shows the eigenvalues. You know, the values that pertain to, you know, talking about the distribution, I suppose. Now, one thing I think is like, if there's an eigenvalue for each eigenvector, and some of the eigenvalues have, you know, say, the higher values, does that mean that that eigenvector is more representative of the distribution of the matrix? You know, and that's an open question. Like, what would we say if that looked different? You know.
So one of the things that I see fairly frequently is related to this idea of volume, but basically the idea is if you have the spectrum of a matrix and you're treating that as a transformation matrix, okay, then if you think about what's going to happen if I have a starting vector and I apply this matrix repeatedly, okay. So in this case, this is sort of like the undirected graph transition matrix is what they're talking about. So if you're imagining transiting a graph, okay, so you start at a certain point and you walk along where the nodes are connected, you know, those are basically going to be the ones in your transition matrix, okay. And so one thing that you see a lot in graph theory is they're using powers of this transition matrix, okay. And so if you have an adjacency matrix and you square it, and so you have A squared, then that's basically the nodes that are reachable in 2 hops from any original node. And if you find the 5th power of the adjacency matrix, that's the nodes that are reachable in 5 hops, but it's not just ones and zeros. It actually is telling you how many different ways you can reach each one of those nodes in 5 hops, okay? So it's this concept that actually, they have a very different explanation, but this concept underlies, for example, the original PageRank algorithm, okay? The idea that if you have an important website, then it's more likely that more people will link to your website, and there are more ways to get there in many hops. And so then you can think of Tony mentioned like Markov chains. You could think of like if you did this infinitely long, then you would end up with a stable distribution of the relative frequencies of all the websites. And that frequency is the PageRank.
So what you could do here is, because this is the eigenvalues is here, and A is then diagonalizable, if I'm not mistaken, then to compute this really quickly, I mean, you could just, you know, raise the Eigenspectrum to, you know, power 5 and then multiply it by the eigenvectors on either side, and then you get back an adjacency matrix, except it's more you can get in 5 hops.
So that's a fast way to calculate powers of any given matrix. Yes, absolutely. But the other thing that I see a lot of is really not as much the full spectrum, but just looking at the largest absolute value eigenvector. So when you're doing deep learning and you have lots and lots of matrix multiplies stacked one after the other, after the other, after the other, okay? They're not all identical, but if you say they have similar spectra, okay? typically what's going to happen is if the largest eigenvalue is, say, 5, and that's that's typical of your deep neural network, then that means that you run the risk that there's a vector that becomes 5 times bigger after it goes through each layer. Because the eigenvalue is 5, then the norm of that vector will grow by a factor of 5. And so then what you can get is you can get numerical overflow from your floating point in both that that value as well as in its gradients. And you have the reverse problem. If the largest absolute value eigenvector you have is 1/5, 0.2, then your value is going to keep getting smaller and smaller, and you run the risk of floating point underflow. And since your gradients are usually a lot smaller than the magnitude of your actual values, you're much faster likely to get numerical underflow. So when you think about why is it we have so many normalization layers in today's modern neural network architectures, it's pretty much because we're trying to keep everything near 1.0 so that we don't get numerical overflow and we don't get numerical underflow. Mathematically, conceptually, a neural network will work with any magnitude values. You can start with 10 to the 500 and just run it, and you'll get whatever numbers that are 10 to the 600. But if you're using IEEE floating point, then you've got to keep things in a much more narrow range. Does that make sense?
Yeah, that's really interesting. Does anyone else have any insight they want to add to this?
The question, if you mentioned, if you look in the middle of the paragraph, the connectivity matrix is not symmetric, which implies the eigenvalues may not be real value. Do you have any insight on that?
Does it say that they're not?
Yeah, so the original brain map that they did, the neurons, right, in your nervous system are one directional. So they basically created an undirected connectivity map, and then it's going to be symmetric, and then all the stuff they talk about in the chapter, symmetric matrices have lots of convenient properties like real value to eigenvalues. But in general, a generic matrix wouldn't. And so the directed adjacency graph is not guaranteed to have real valued eigenvalues. I don't know enough about this field to know if people where it's not an introductory text like this, if they're like, yeah, we didn't do that simplification and we have some way of analyzing the complex eigenvalues, I have no idea. But for a simple chart like B at the top of Liam's slide, it's much easier. If all the eigenvalues are real, then you can just easily plot them.
Well, that does remind me of, SVD, and specifically reduced SVD, and the fact that you get like some, negative, or you get some complex eigenvalues out of that, that you just kind of ignore. I kind of wonder, like if we don't ignore it, what happens at that point?
I think it's a good point, and that's why perhaps you actually see SVD used a lot more than eigendecomposition, because it's more general and it has those strengths. The other thing, quick comment I'll make, is that if you're given a matrix that comes from the real world, not from some mathematical formula, the odds of it being low rank when you do 32-bit floating point precision are infinitesimally small. Okay, so even if you have columns that are multiples of one another, they may not be in the 16th decimal place exact multiples. So there'll be a slight rounding or up or down somewhere. And for that reason, when you look at the spectrum of data based on like actual measurements from a chemistry lab or biology experiments or whatever, something that's low rank, instead what you'll see is just very, very small eigenvalues. So if you said, oh, I have this 8-dimensional matrix and my eigenvalues are, 3, 2, 1, 0.8, 0.6, 0.2, and 10 to the minus 7, and 3 times 10 to the minus 19. Those last few really, really tiny ones are probably fake rounding errors, and you probably have a low rank actual matrix. Yeah.
I just want to ask about the graph. Is the reason there's no shades of gray is because it's connectivity and doesn't indicate the direction, and therefore we can't indicate a weight? Like, I was just surprised that there's no weight between like the significance and one guy.
So, well, I mean, the reason
Here,
On A or B?
oh, I'm sorry, black and white, the one on the left.
Yeah, that's just because it's a 1 or a 0. It's a binary
Right.
value. Yeah.
I don't know if the actual biologists have more nuanced analysis that they do, but for the purpose of this chapter, they just said connected or not, 1 or 0, and that's to answer your question why there's no grays. White if they're connected, and otherwise, it's 100% black. Yeah.
I mean, I think, I think the principles are generally the same. But, stop me if there's any nuance to that. I don't know. Okay. Yeah. So, anything else we want to talk about before I move on to the code pertaining to this? Okay. Move on to the code then, because I have something kind of interesting. This is off book. I'm sorry, Ted. But, so we were talking about the characteristic polynomial, right? And how that's essentially like or you have to find like the roots of this determinant a minus lambda I function, essentially. So if you want to calculate that, say in Python, what you could do is you could make it into a minimization function. So you need to like iterate it over and over again until you get a very, very low value and you say, hey, that's the root, essentially. And, in SciPy, you can use like fsolve for that, just like some general minimization function. But there's actually, obviously there are more clever ways to do that, and I want to just talk about one of them here. I think I might have accidentally just typed something in there.
Control Z.
It's great. But you actually
Control Z.
I am really scared to press Control Z. I'm not gonna lie. No. We're gonna maybe after the presentation. Okay. So I want to talk about this QR algorithm, which is actually used pretty frequently when it comes to like solving systems of linear equations and finding eigenvalues and eigenvectors. I just want to show that there are actually different types of decompositions and how these principles kind of apply here. So if you're not familiar with QR decomposition, essentially for any matrix, you can decompose it into an orthogonal matrix Q, which represents like a basis, right, more or less. And then R is an upper triangular matrix. So it has all zeros underneath the diagonal. So what you can do is, if you'll remember that A equals P minus 1 DP, D is similar. So D has the same eigenvalues, it has the same eigenvectors. So instead of minimizing the function itself and trying to find the roots, we minimize it more or less as a matrix all at once. And how we do that is we get this QR decomposition with this basis and this R, which is a similar matrix, and then we put it through the reverse. So we do something like RQ, R, etc., and we keep on getting similar matrices. And so as that happens, it starts to minimize to where the eigenvalues are actually found on the diagonal there of this inner similar matrix. And so basically you're just doing the same thing as like minimizing the roots, but you're doing it as a matrix. And you're also just solving it, this PDP function. And then all you have to do is keep track of all these Qs like QRQ, or yes, QRQ, right? You have to keep track of all these Qs and add them up so that when you are done, you get all the diagonals being these eigenvalues, and the sum of all these Q matrices as being the eigenvectors. This is actually what SciPy uses under the hood. The only difference being is that I have to set a threshold, and there is a fancy way that is named after a mathematician with a long name of actually setting that threshold themselves automatically. So I actually had to, in some of these exercises, set the threshold myself. But I just thought that this was really interesting. Really quick, does anyone have anything to say about this or want to ask anything? Or yeah, it's kind of awkward. So gonna move on. Anyways, so yeah, but as you can see, it does the same thing as SciPy. So these are the answers to 4.3, 4.4. I do not give them in, obviously, in like what is it, irrational form, right? Yeah, I don't give them in irrational form. Obviously, they're just like a combination of numbers. But see, I actually have to set the threshold here instead of just letting that be automatic. So yeah, did anyone get any different answers? Feel free to pull out a calculator. Okay. Well, in any case, I just thought that was really cool, and I'm gonna move on to the next thing. So let me get back to this. That's why I was doing that. Okay. So eigenvalues, eigenvectors, and then diagonalization, which I found surprising that there were a lot of exercises having to do with diagonalization. It kind of made me wonder, why is diagonalization so important? And if a matrix is diagonalizable, right, then the geometric multiplicity is equal to the algebraic multiplicity. That is, there's no the dimensions of the eigenspace is equal to how often the eigenvalues are found. And then computations are much faster, such as in that matrix of eigenvalues we saw in that last slide. You could just raise it a couple powers, and then with its eigenspace you could get a matrix that is exponentiated up very, very quickly, as well as a lot of other computations. But basically, what I see it as is if the reason if it's diagonalizable, then it's similar to this diagonal matrix. And if it's not diagonalizable, then this equation does not really hold. So it cannot be reduced down to this similar matrix of eigenvalues. I do say it's a key concept in PCA. It alluded to why it's a key concept in PCA. And my knowledge of PCA is eigenvalues, eigenvectors, how it pertains to that. But I'm not actually familiar with why diagonalization is a key concept in there yet. But we'll find out. But yeah, actually, I'm going to open this up to people. Do you, where people have seen diagonalizable or diagonalization, happening, maybe outside of, constituent elements of other algorithms, or, because how I see it is it is a statement about the stability of a particular matrix. Like if it's diagonalizable, then it doesn't have, planar null spaces or anything like that, so I don't know. Open that up to the group.
If you're gonna take the exponential of a matrix, then you only diagonalize it because it makes it trivial to do to take the exponential. Now, if you ask me, why would you take the exponential? I have to think about that a little more. But I mean, it's just saying that to get the diagonals just are if you have the directions, if you have a linear transformation, the matrix is a linear transformation, then there are directions where you just get an expansion or contraction. In that direction, those are the eigenvalues, and they're geometrically, they're variants. And so the P's are just saying in some other, there is a choice of basis where the linear transformation is just those expansion and contraction values. And then the other basis, you have that singular transform to get from there to how the linear transformation is represented in that basis.
Yeah, the basis of the eigenvectors. So the would you call it an eigenbasis? I mean, eigenspace, regardless. Yeah, I think it's a fascinating concept, and it can be used for very quick computations. In the code, I kind of cheated. Well, I didn't really cheat, but I just come on. I just checked if the rank of the matrix of the eigenvectors was equal to the shape of the original matrix. Basically, like whether or not the eigenvectors form a basis in Rn, which is the rank of the matrix. And I think that's important. What in the text, it didn't really give any examples of like when an eigenspace has less than the number of vectors in A, but it still forms an orthogonal, or it still forms a basis in Rn. They didn't really give any examples of that, so I don't really know. I don't think that's possible, is it?
You mentioned that you can use a branch net procedure to get an orthogonal set, even if the original one is not orthogonal, because
if you have multiplicity 2 and it defines a plane, then you can find. But I think the problem is that sometimes it's not a plane. So they're like collinear, and so then you're up the creek. So I'm thinking if you, I'm not sure. I think maybe if you have like a pair of complex eigenvalues, then I don't know. Yeah, I cannot quickly give you that.
Yeah, I couldn't.
I thought there was an example in the book of something that was the eigenvalue was repeated 2 times, but there were not 2 independent eigenvectors. But there was only one eigenvector.
This computer is on its last legs. Oh, all right. Anyways.
Yeah, and for what it's worth, like to your earlier question, I haven't seen diagonalization as something that anybody cared of in and of itself. It was a tool to either some other technique like SVD, or it was a tool to what you said, fast powers, but it was never the end result in and of itself. As opposed to like eigenvalues, that can be the end result itself. Like I want to know what is the largest eigenvalue. And it's not in order to something else, it's just I actually want to know that. I don't know that I've ever actually seen anybody say I want the diagonalization. Full stop.
Interesting. Well, that's good to know.
One last thing on that. Now, I don't know if it's actually true or not, but my intuition would be that it's related to, is this a combination or a permutation situation? Where does it matter as you add red, green, and blue, the order that you add them to get the color in the end? Your unique color space, it doesn't matter, because it's the same way. But there may be cases where it does have a different outcome.
Can you give an example of that?
No.
Decomposition. Order, and that can produce a completely different result. So that's a step that, you know, is a little bit unintuitive. Is that kind of what you're talking about?
No, I can't articulate. I was hoping someone else would be able to
It
say, yes,
seems
that's
really-
based on this math thing that you didn't know.
It seems really profound. Okay, all right.
Let's move on. I think we should spend a good amount of time on SVD. I think
Okay,
that's really,
yes.
really important.
Yes, of course. All right. Yeah, so anyways, just really quick, these are my answers to 4.5 and 4.6. You know, and then, yes. And then just quick, true, false, 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 true. And then for exercise 4.7, I kind of tried to, you know, print out like why it would not be diagonalizable. But, and I think for this, I basically just like tried to solve this. And then I tried to check that D in the center of this equation was diagonal. They just turned out they just weren't diagonal. It just says, you know, D is not diagonal. So, I mean, you know, short of like, you know, going and doing it by hand, you know, that's all I got as far as that goes. So,
If I could jump in real quick, I think one of the points of exercise 4.7 is to show you that your answers for invertible and your answers for diagonalizable are independent of each other. They're not the same, and it's also not a subset. That there are some that are invertible but not diagonalizable, and there's some that are diagonalizable but not invertible. So they're just completely independent concepts. You can be one but not the other, and the other not the one. So neither is a subset of the other.
So for diagonalization, we mean that all the eigenvalues will be different from each other, right? So if you have
No. Having unique eigenvalues is sufficient for diagonalizability, but is not the only matrices that are diagonalizable. There are ones with repeated eigenvalues that are diagonalizable because you can find a full basis for the repeated eigenvalues. I just cannot, off the top of my head, give a quick example of when you can and when you can't find a basis for the repeated eigenvalues.
well, if you had like say you had like a diagonal D matrix of all the eigenvalues, and you had like the eigenvalue of 2 appear twice, like as 2 separate values, and then in the eigenvector matrix you had like any 2 vectors in that plane that you mentioned, that it could be, but it could be ambiguous, I suppose.
Like, I don't have the intuition why, but a rotation matrix is very much invertible. You can undo a rotation. Okay, you can reverse it. Okay, no rotation matrices are diagonalizable. Okay, but I don't have I can't explain it to you, the intuition. It just, that was mentioned, I think, towards the end. And if you try it, you'll see that is the case. But
No rotation matrices are diagonalizable.
all of their eigenvalues are either 1 or -1. So it's easy to come up with a rotation matrix where the only eigenvalue is 1 and it's with multiplicity n. So there's n copies of 1 as the eigenvalue. And there's something about it that you don't get a full rank basis for that eigenspace.
So in 2 dimensions, there are no vectors unaffected by rotation.
Okay, that's a good intuition. Yeah. So if an eigenvalue, right, says that you're just going to wind up with something pointing in the same direction, and it's either the same size or shorter or longer, but in the same direction. And with the rotation, that will just never happen, except if you give it the 0 vector as an input. So that's why rotation matrices are an example of something that's full rank, but it is not diagonalizable. And they're not even like some kind of like weird matrix, right? It's not like it collapses the result down to a lower number of dimensions. It's not that it's not full rank. It's everything you want. It's full rank. It's, you know, but you can't diagonalize it.
That's fascinating.
So is it amount doing rotation about the null space?
In linear algebra, rotations are always about the origin. Okay, they're never off to the side.
Yeah, I guess I'm trying to kind of trying to see what the vectors are.
Rotation should rotate every vector, every basic vector. If it is one of this basic vector is stable, then it will give non-zero eigenvalue. I mean positive eigenvalue. Also, other positive value, other eigenvalues will be. Okay, so at least one of eigenvalues will be not just real. It will be
Right. So it's not going to have.
okay.
Yeah, it's not going to have full rank because one of them is going to be not real.
Okay.
Okay.
Yes.
Okay. All right. Cool. Appreciate that. Okay. Let me get back to this, and hopefully I don't like accidentally delete this every time I go back and forth. All right. Cool. All right. Diagonalization, etc. Let's go to singular value decomposition. So really quick, in the text, they went over, you know, how the author defined SVD. And then he also talked about reduced SVD, where the singular value matrix is actually square. He didn't go into a lot of detail about that, but I think that that's really valuable for like reading papers, and, you know, they might be using a reduced form a lot. Similar to like, you know, how, I don't know, maybe they use linear transformation to refer to like an affine transformation or something like that. But I think the thing that like tripped me up a couple times is the fact that the v vector at the end of the equation, a equals u sigma vt, represents the space or the basis of the domain, whereas u represents the basis of the codomain. In that case, being the rows, and, you know, the v representing the columns. So I think it was interesting that they went through the example, right, and you could see in this. Let me get my mouse over here. You're able to kind of isolate in this like user space, or the space of like, you know, the possible users. You can see that Star Wars and Blade Runner, not users, movies. You can see that Star Wars and Blade Runner have similar values and are kind of part of maybe the same genre. And then you can also see that Allie and Beatrix have, you know, similar tastes in movies. But you also see this, you know, the secondary kind of category that might exist here. And these singular values kind of represent the scale. So the way I kind of see it is V is and U are the distributions of the domain and the codomain, and then the singular values represent the scale by which V transforms into U, the U being the image of V, which is something that they talked about in the examples. And they also call this the fundamental theorem of linear algebra. And then just a little identity here that for symmetric positive definite matrices, the eigendecomposition, right, is equal to the singular value decomposition. And that kind of makes sense, you know, because, you know, no complex values, positive, symmetric, you know, square, etc. Yeah, kind of makes intuitive sense. There's a lot to cover when it comes to singular value decomposition. I feel like this is definitely used a lot. Does anyone have any questions pertaining to SVD or their definition in the text?
Did you grab that picture? I don't know if you have another slide, the one that had the geometric intuition for the SVD.
I did not.
I really liked that. I think that was like figure 412 or something like that. But it's got the 4 pictures, right? And if you start with a circle, and then they show, you know, the arrows where basically the V transforms your basis, you change a basis, and then the sigma matrix moves to the right, and it scales along each axis. And then the U matrix does another change of basis. I had previously read this chapter before, so not this time, but the first time I read this chapter, I spent a really long time looking at that diagram and trying to understand it and whatnot. And ultimately, I found it very helpful. I don't know if I'm jumping ahead, but there is this intuition that I have, and I'll say it in a certain way, which hopefully makes sense to people. But I think you guys know that if you start out with a vector, we'll just say length 3, just for simplicity, you know, R3, okay, and you do a linear operation on it, so 2 times the first one, 3 times the second one, 4 times whatever, and then you do another one, no matter how many of those you do, you could have just boiled it down to 1 linear operation. That composition of linear operations nets you with just a linear operation. So there's a way that you could have pre-computed all 100 of those steps, and in 1 step you could have just done a linear operation to get the exact same answer. You guys familiar with that property of linear transformation?
I actually read about that when I started learning deep learning, because that's actually a reason why we add nonlinearity functions. Otherwise, if we just multiply matrices, it's equal to multiplying by just 1 matrix.
That's right. You could have just somehow pre-computed the effect of those 100 matrices without the nonlinearity, and you get nothing.
And for a real-world example of that, Rubik's Cube can be solved from any position in no more than 17 moves. But the speed cubers don't do that because it's much faster for them to apply the algorithm to the physical system.
Yeah. So with the singular value decomposition, what that's saying is that any linear transformation, because the matrix represents a linear transformation, any linear transformation can be broken down into 3 steps. Find a very particular special basis, okay, and then in that basis, you only expand or contract things along the axes, okay, and then you rotate it back to your new basis, okay. That was like one good intuition for me, but there's this other part that I realized is, let's talk again in R3, okay, so like you have a 3-dimensional vector, you can visualize this, and now I apply a very large matrix to it, like a 20 by 3 matrix to do a linear transformation, okay? In the same way that doing 20 linear operations on 1 vector is the equivalent of just doing 1, okay? If you have a 20 by 3, the net effect of it has to boil down to the same thing as a 3 by 3 in 1 sense, okay? So the idea is that if you look at the definition of singular value decomposition is all you're doing is changing it to a new 3x3 basis and adding a whole bunch of zeros. And you're only scaling it in 3 dimensions. And then you're rotating it to a new basis. Okay. So this concept of rank is, for me, and I hope this is making sense for you. The concept of rank for me is very intrinsically tied to this concept of that composition of linear functions gives you just a linear function. So in my original example, I'm just doing a rank 1 operation, 2 times this one, 3 times that one, 5 times the other one. And no matter how many rank 1 operations you successively do without a nonlinearity in between, it can be collapsed down to just a single rank 1 operation. So what I'm saying is if you have a 20x3 matrix, you have rank 3. It doesn't matter if you do 20 rank 3 operations, it can get boiled down to a single rank 3 operation. And so all you need to do, conceptually, you could boil it down to a single rank 3 operation, and then basically all you're doing is finding the basis in which you're scaling things, and then doing another change of basis into the final space. Another way I found of saying this same phenomenon is that if you start with, let's say, in 2D, a circle, okay? If you multiply it by a 2x2 matrix, you're going to get an ellipse. I mean, it could be degenerate. It could be a circle where it's symmetrical. It could be a line, but it's going to be ellipse. You can never get a parabola. You can never get something that's not symmetrical like an ellipse. You're always going to get an ellipse. Okay. The crazy thing is, if you multiply instead by a 2x2, a 20x2, you're still going to get an ellipse. It'll be oriented in 20 dimensions in some way. You don't know what angle it will be at, what plane its orientation will be, but fundamentally, it's still going to be an ellipse. That's one of the implications of this decomposition. It says that if you start with rank 2, a 20x2 matrix, it can be at most rank 2. And therefore, the most you can do to a circle is you turn it into an ellipse. And so everything else is just what direction do you stretch it, and then where do you plop that ellipse in your new 20-dimensional space. That's how I would say, in lay terms, that's what the SVD theorem is telling you, is that a rank 2 matrix can at most do that stretching in 2 dimensions. And you just have to figure out the orientations from your source and the orientation from your destination.
For an even more trivial example, y equals mx plus b. If b is 1 plus 2 plus 3 plus 4, you could do 4 transformations, but ultimately it comes down to it's a constant.
Right. So that's this function of linear operations being sort of closed under linear operations, right? You wind up with something, and so you can always kind of reduce it. So anyway, so for me, that sort of is the way in which I feel like rank sort of underlies this closedness under linear operations. Rank is sort of the ceiling of the complexity of what you are doing. And as soon as you say I'm limited to rank 2, it just doesn't matter what you do. You're going to wind up with a very simple rank 2 object. And so you do LoRa with rank 2 on a 256 by 256 matrix, right? All we're saying is it's a very simple ellipse, a 2-dimensional object, but it's oriented in this ginormous 256-dimensional space.
Yeah, and I mean, it makes a lot of sense because I mean, like that singular value matrix can only have as many elements as there are rank in the original matrix. So it is just like a stretching operation from one basis to another basis. One thing I wonder about actually is, so I did actually change over to the code here. Following, like, basically the formula that was laid out in the book, I know there's faster ways to do it, but again, I didn't want to lose the plot too much, as fascinating as that might be. I wanted to hang on to this particular thought really quick, though, and I wanted to kind of ask, though, why, for one, there we go. Okay, but I also wanted to ask, like, so we have these complex singular values that we kind of just ignore, and also singular values that are so small. Because here, I actually had to add, like, if it rounded, it's 0, but also like that there are these negative singular values that come out because they're negative eigenvalues, and I kind of wonder, like, what the significance of those are pertaining to this, like, stretching operation, if there is one.
I mean, simplistically, you can take a circle and just stretch it horizontally into an ellipse by a factor of 2. Okay, and then that will have a value of 2 associated with it. You could also stretch it by a factor of 2 and then take a mirror image horizontally, and that would have a value of -2 associated with it. They look like, at first blush, like the same ellipse, but if your circle didn't start out as just a circle, if you sort of colored it so that it was like a rainbow, right, then you would very quickly see that one ellipse has red on the right and the other ellipse has red on the left.
Okay, but it still boils down to the same stretching operation, essentially. It's just you can also, define it as a rotation in a complex direction or something like that.
Think of it as a clock face.
Well, like
You
flipping.
can stretch it or spin it, what have you. It's a different operation, and it's a different thing.
I don't really have an intuition for, like, the determinant being positive, negative, for these values being positive, negative. Like, what the signed volume means doesn't really mean much to me. All I know is that if you flip it once in any direction, it flips the sign. Okay, how do you define the number of flips in 3D? Like, mechanically, I know you can do it, but I have no intuition.
If you get a negative volume, it means you get the handedness of your basis is up the opposite of.
Thank you. Yeah, opposite handedness. But it doesn't mean that you can get there in one flip. It might actually require you 3 flips if it's a higher dimensional object. So it's your handedness, it's your even odd, but I don't find it terribly meaningful, helpful, or anything.
Yeah, I remember on that, like, determinant slide, like, that's the kind of thing that I did, like, flipping 2 of the row vectors, like, changes the sign. Like, that's something that I remember I found an intuition for it like 3 weeks ago, and then I forgot. But it does kind of make sense, though. I mean, now I think about it, if, like, the orientation matters in the sign, then you just flip the direction of them, kind of. But yeah, so, like, back to, I want to talk about the methodology that he uses, because again, there are many faster ways, and this would break down in, like, large matrices pretty fast. I forget, I think, like, the complexity for this is, like, maybe n squared or cubic, if I'm not mistaken. Might be cubic. I figured that out at some point, but it's not relevant. Anyways, so in order to find, like, the basis of the domain, which is V, basically he just takes, like, the ATA, or the eigenbasis of ATA, and I think he just does that to, like, square the matrix, and then he takes the, actually, what is it? Forget about this. Yes. Okay, so you take the eigendecomposition of the squared matrix because it's square. You place the basically the e-values or the eigenvalues as the singular values into the matrix. And then you create the U space as the image of V with respect to those singular values, which is just the projection of, what's in V scaled into U. And there's some intuition actually going back to the rank nullity theorem there, that like the ranks of these two things might be dependent, but I can't quite articulate what that might be. But I think it's fascinating that like U represents the image of V projected by these scaling factors. So fortunately, I just did exactly what he said in the book. Didn't have to get any more fancy with that. And I basically just like computed these things, and I made sure it was the same as the original. So this is this an exercise? Okay, so this is the book example, and then for exercise 4.8, probably kind of difficult to check the irrational version of this, the non-decimal version of this. But if anyone wants to, take a look.
The bottom left looks finicky.
Bottom left? What do you mean?
The negative 17.
Oh no, that's just a very small number. That's basically 0 at that point. Is that what we're talking about?
Yeah, it might be a 0.
Yeah. I mean, I had to round it. I mean, it is exactly finicky. There are some very, very small values here. Or actually not there, just this one. But that's why I,
The threshold on
which one?
on the previous slide, a while back, you had set the threshold to negative 12, which is why negative 17 jumped down.
Oh yeah, no, I see. No, well that was let me see.
That was a different threshold. Yeah.
Yeah, no, that's the threshold, and actually, I'm using the eigenvalue from SciPy there, just because it's a little cleaner. So I don't actually know what the threshold is being set, but as you can see, it's not actually coming in oh wait, no, it is coming in the domain. So that might be something from SciPy actually, if I'm not mistaken. As I said, it gets set dynamically, and I think my default is like to the negative 15, so I don't know. But so this, these are the examples I got. I made sure that you can multiply them together, or you can take the product of them and get the same matrix in return. So yeah. Any other closing questions or comments regarding SVD? I know it's a very pertinent sort of topic of discussion, but if anyone else has anything to say about that?
I like the analogy from the meeting at Novo, where you had man is to king as woman is to queen. So if you're thinking of word spaces, okay, we have the gender, there's one axis, and then we have the levels of power. And if you want to tie that back to the sign, then you could have a negative sign being king is to men as man is to boy, or something like that.
Interesting. Yeah. No, that's definitely a good intuition. It's kind of relating different elements in one space to another space. Would you say like the singular values are like the degree to which they relate, or?
I would think that it's more like the way I would view it is, hey, in this example, I've created two axes. We've got a gender axis and we've got a power or social strata axis. And you can have as many dimensions as you want to apply to those and scale along those lines. So for the scale, I would go more as a step from boy to man, man to king, or man to lord, lord to king to emperor, and to have some sort of factor along those lines. Well, for a weirder example, we see basically 3 colors of RGB. Mantis shrimp see 12 or 14 different color spectrums and spaces. So like when we look at a pigeon, it's dull gray, but when pigeons are looking at each other, they see very UV modeled patterns
iridescence beyond what we would see.
Interesting. And then that would be like the image of our perception, essentially.
And going back to the 2D matrix, if it's a circle to us, we're not seeing the other color spectrums because those transformations don't matter to us.
Right. Yeah. No, that's a really good
In
intuition.
Ted's example, where you have the ellipse oriented in the higher dimensional space, is one of those matrices the rotation matrix for that space?
An orthogonal matrix is a rotation matrix. Yes, I think with an optional flip. So assigned rotation matrix.
U and V are orthogonal, right?
Yeah.
Okay.
And
That's what, yeah.
orthonormal is the convenient form.
Is it orthonormal? Each one? Or U and V are they orthonormal? Normal? Oh.
Or they've chosen such that they are ortho.
Oh. Okay. So one of the I think the interesting application of SVD so far, well, I found this part really fascinating, was the rank K approximation. And so, basically, for each, column and row, or I'm sorry, for each vector in U and V in the domain space and the codomain space, taking the outer product of those two to, create, and say, m by n matrix, and then multiplying it by its corresponding singular value, comes up with this approximation of the underlying matrix, based on some specific property. And I found this incredibly fascinating. And we can kind of see here, what? There we go. We can kind of see here that, we can almost see individual features. Almost to me, it seems like if this is each, one sort of relationship between things in this image, this kind of corresponds almost to the lighting, whereas this one kind of corresponds to the more minute features, probably a singular value with a much, with a much lesser, a smaller value than A1. So here, and I also did this as well in the code, but it also gave us this way of determining basically the maximum length that any vector can have in this transformation, as well as why are my images over? As well as a metric to understand how good a particular approximation is, which is Eckhart-Young theorem, and the spectral norm as well. I didn't calculate those two things, but I, but I think it'd be interesting to calculate them. So, and then I just want to go to the code really quick as far as.
I have a question about the spectral norm, the max. The spectral norm is the max of the L2 norm of A multiplied by X divided by L2 norm of X. So max, we need this max just because to have a spectral norm like a positive value, not a negative one, right? Because when we take a square root, it just could be positive or negative, and we want just it to have a plus sign. This is what we really want.
Yeah, it's the absolute value. It's it's the scaling factor, and so really it's just the absolute value of the largest eigenvalue.
Didn't they take the Euclidean norm of this one?
Yeah, they're taking Euclidean norm.
Yeah, or I mean, it could probably work with any norm.
Yeah. Well, we get different answers to use different norms, but I mean, it's what you said. The norm keeps you in positive numbers, and if you have an eigenvector, then when you multiply it by a, it will be turned into exactly its corresponding lambda times itself. Okay, so let's say your eigenvalues were like 8, 4, 2, and 1. Okay, so the first eigenvector will get turned into 8 times itself. The second eigenvector will get turned into 4 times itself. The third eigenvector will get turned into double itself. If you pick a vector that is, I'm going to use the equating term, 45 degrees, exactly halfway between the first and the second eigenvector, okay, it will be exactly 6 times, because I know one is 8, the other's 4, so I know that one's going to be 6 times. It'll be in a different direction, but it'll be 6 times its length. That make sense?
I'm not sure I followed completely.
Okay, but the idea is that if you think of a circle expanding into an ellipse, the axes of the ellipse tell you what the expansion is in each of those directions, and in between, it's always going to be the minor axis of the ellipse is always the minimum expansion factor, and the major axis is always the maximum expansion factor. And so when you're aligned with either of those axes, you get the minimum or the maximum, and everything else is in between.
That makes sense.
Yeah, and so then you can extend that, although geometrically it's hard to picture, you can extend that to as many dimensions. And so that's the way that I now think of eigenvalues, which I didn't understand when I took the college class and just did the bare minimum to determine the assignments. You know, like, oh, this is really describing exactly how every vector is transformed. And when you have a vector that's in between the first and the second eigenvector, you just use those as a basis to say, oh, well, this is 1 times eigenvector 1 plus 1 times eigenvector 2. And then you know that eigenvector 1 is going to get expanded 8 times. Eigenvector 2 is going to get expanded 4 times. And then you can just square that and figure out like what's the exact value. I think I said 6 and I think I'm wrong. Actually, it should be like whatever, the square root of I thought 64 plus 36, whatever. So it'll be 5, whatever. But like you get my drift.
I was about to make a wrong connection, assuming that 6. So you're saying, oh, so it's essentially you're taking the average of these in a 3D space. That's why it's not 0.707 for the sine of 45 cosine 45.3. No.
Yeah. So I may have misspoken, but the idea is that you can always represent any vector as just the in terms of its basis. In this case, we use the eigenbasis. So then it's something that's scaled 8 times, some component that's scaled 4, some component that's scaled 1, depending on how much of each of those. Then you can just sum that up and take the square root, and that'll tell you the L2 norm, how much it grows in length. Make sense? Yeah. So it's easiest when you just have one, and then that theorem that you had basically shows that if you take out the largest eigenvalue, then what you're going to get left with is the second largest eigenvalue.
Okay. I think yeah.
And if you take out the first 2, what you're going to get left with is the third eigenvalue.
Oh my goodness. I'm trying to move the images from between different Linux versions. It definitely messes with some stuff. I did have informative text there, I swear. Anyways, so yeah, computing this, rank R, rank K approximation, pretty straightforward. For each, row or column, you find the outer product, multiply it by the singular value, and then you get like some sort of approximation. So this is basically the answer to 410 with way more decimals than needs to have, but that's okay. I think it's kind of fascinating that what was this? Okay, so if having this starting point, these two, this column for the rank 1 approximation is essentially useless. Like it's very, very small value. You could call it 0, honestly. And then for this column, right, it's 2 and -2, and those are, you know, I don't know. These seem like seems like there's more of a correlation here than there is here. You know, maybe that's just like eyeballing it, what it kind of looks like. But why this rank 1 approximation is kind of picking up these features and not these ones. So, yeah. Does anyone have anything else to add to like rank K approximations? You know, one thing I'm actually kind of curious about is like in production. I know that there are some people in here with like experience who are currently working in computer vision, and I'm kind of curious like at what point in the pipeline this happens, you know, or when this is kind of useful, you know. And I think you know, open question. Kind of curious about that.
Well, when you first saw this image, if you look at the bottom route, which is essentially mapping the grass, in computer gaming graphics, that's the type of thing that can be, you don't have to map that, you're going to randomly procedurally generate it, because no one's looking to see if that blade of grass has always been to the left or the right. Whereas the larger block, specifically in the top right, is, hey, here's where we need our high definition textures, our lighting, other maps kind of stuff.
So in computer graphics and rendering, do you have like you do that programmatically, or is that just for like analysis? You know?
This isn't through machine learning. This is for like game development side of things.
So just for analysis, you pull it up and you're like, here are the features, or here are the larger features, the more, you know.
Yeah, I don't know that they actually do that, but when I looked at that, because I worked in a bunch of different domains, it's like, oh, that's where these values would get mapped out. And looking at this graphic, I would say, hey, that's how we could use this to determine what we need large textures for. And I would guess that probably NVIDIA is doing that for their texture compression in the 5000 series. I don't know that they are, but.
So the correlation that helps in that particular situation is that the things that you don't care about are generally all the high frequency features. Okay. So you basically
these
can
lower
decompose
features
down
here, right?
to the lower frequency features like rock versus sky, right? Whereas the grass, you can see it's a much higher frequency changing back and forth between each blade of grass, right? So one place where I've seen this pop up in ML is people have been trying to build image generators. And so you have something like VQGAN, where you have a discriminator and you have this discriminative loss. The discriminative loss is applied patch-wise. It'll only look at like small individual 16 by 16 patches of your image successfully. And by looking at a very small section, it's looking at very high frequency features, right? It's not saying macro over the course of this whole picture is something changing. It's just saying in this tiny little patch, how is something changing, okay? And basically what happens is when you add a GAN discriminative loss, it solves the blurriness problem, okay? So your models generally for grass will just output this blurry green mass. And by adding a discriminative loss, it'll have the right kinds of features that look realistic for grass. But the grass might not actually be even remotely identical to the original grass in your image. It's fake grass that humans don't pay attention to, okay? So when you're generating image, and if you're using things like perceptual loss to tune this model, then that's well tuned to what do we care about when you say, give me a picture of a puppy dog, whatever, holding a sword, fighting a dragon, right? But it turns out when you then say, I want to use these models, which are really advanced, and do weather prediction, all of a sudden saying that you can fake the high frequency stuff and saying that you're going to emphasize human perception versus mean squared numeric accuracy means that if you just literally lift and shift and take an image generation model and use it for a scientific thing to like predict, you know, weather or you know, the density of your whatever, you will have problems right off the bat that you have to now go back and correct for because
Your 3D printed bottle leaks.
yeah. So anyway, that's one place where I've seen like that particular phenomenon is that like, yeah, you can figure out what are the basis things of like what the human brain and the human eye care about the most. And if you highly optimize that, then if you're suddenly are dealing with a different domain like weather, or I guess hypothetically, if you're doing pigeon can, then you care about other things.
Interesting. Okay. Well, cool.
One other thing on this, there's an internet meme called, there's a webcomic in one of their episodes, was a very serious one, and it was about loss. And it's the kind of meme where you have a vertical line, and a shorter vertical line, another vertical line, and then vertical line, horizontal line. And it's a extremely reduced form of, hey, anyone who's familiar with that graphic sees the 4 lines can recognize that as a reference to the original picture.
Is that an XKCD or something?
Not XCC, Control-Alt-Delete.
Yeah. All right. Well,
Thanks, Liam.
of course, that is all I've got. Thank you everyone for participating and sharing your experiences as well. Definitely. I'm going to shut this off before it catches fire.